Okay, we're going to call this part 3. It's really mostly part of part 2. In part 1, we looked at the rebar for a slab floor, a suspended slab. That's one that sits on top of the walls. It's like the ceiling of your first floor and the floor of your second floor. And that was a floor slab. And now we're going to do beams. We're going to do 2 examples. And we're going to put something on these beams. I'm going to put a floor on both of them. And we're going to do 2 calculations with the same load on the beam, though it may not be in reality if you're building something. But the thing is to show the relationship of a tall beam versus a flatter beam of the exact same cross-sectional area and same number of rebars. But anyway, we're gonna look at this. First, we're gonna design it to find out how many rebars are needed with the load, and then we could draw them onto the beam. But first, we're going to calculate how many you need. If you had a beam already designed and you run through the same calculation, it'll tell you whether it's strong enough and by how much it's under or over. You know, percentage of what the actual is. You just divide one into the other and get a percent. But we're gonna use the same concrete, same length beam, same weight of concrete floor. We'll say call it concrete floor. And of course that one out. Okay. So the other 2 videos on this group have this exact same spreadsheet. It's not a spreadsheet. It's just something that organizes it for me so I don't get confused. I'm 80 years old. So I just put the word part in wide print, and the numbers are in standard narrow print, so they sort of stick out, and also got them above the line so that they stick up, easy to find. I'm just going to read through this, and then we're going to make some conclusions. 114.169 inches of width times 144 inches of length, and times 22.28 inches of thickness. That equals 45,458.7 cubic inches, and this is across the narrow span. This section. Actually, this is the beam. Every place it says slab, it should say beam. I'm just totally lazy, but the numbers are the same. So we got the cubic inches that's in this beam. So we take 45,458.7 cubic inches of beam section across the narrow span, divided by 1,728 cubic inches per cubic foot. That equals 26.31 cubic feet of concrete. 26.31 cubic feet of concrete times 150 pounds per cubic foot equals 3,946 pounds of concrete. Okay, what do we do after that? Okay, I see what I did. I did it in a different order. 3,946 pounds of concrete divided by 2 equals the calculations weight. That's the same as we did at the top, where half is on the ends of something. The other half is divided into basically force of the original. They add back together because you're doing them at the same point, and it makes it over 2. So it's half of the total weight. So 3,946 over 2 equals 1,973 pounds, with the other half of the weight supported on the 2 endpoints. Now we're going to do the surface area, because that's what we're going to put our load on, is the part that's on the top. 14.169 inches of width times 140 inches, that's 12 feet, of length equals 2,040 square inches of surface area. 2,040 square inches of surface area divided by 144 square inches per square foot equals 14.7 square feet of slab area. 14.17 square feet of surface area times 850 pounds per square foot of live load. Now, you'll notice that in the original boldface on here it says 50 pounds. That's 50 pounds for the furniture, your dog, whatever's walking around on the floor. But in this case, we actually have a concrete floor to deal with. Before, the weight of the floor was, we were calculating a floor, 100% of the weight of the floor was there. In this case, we're going to go 850 pounds. 50 of it is the live load, and 800 pounds of it makes up for the concrete that's in the floor. So, if we take the pounds per square foot times the square feet, 12,044 pounds of live load. Sounds like a lot for one poor beam. Okay, 3,946 pounds of dead load plus 12,044 pounds of live load equals 15,990 pounds of total load. 15,990 pounds of total load times a safety factor of 1.5, equally applicable on this. That gives you 23,960 pounds of total load. That's got to be resisted by the steel and the concrete. So 23,986 pounds of total load times the inches of span over 2 gives you a moment of 863,487 inch pounds. And let's run the screen up a little bit. Okay, 863,487 inch pounds, a moment of concrete at half span. It's divided by the distance from the top surface of the slab to the center of the lowest rebars of 19.96 inches. And we'll take a look at that for those who didn't see part 2. So, there's your 19.96959. That's in the center of the rebar to the surface, which would crush if it was pushing down from the top. So that's your lever arm. We know how many total pounds it is. If we divide it, we know how many pounds we have to resist, and if we divide it by the distance, we come out with the pounds of the steel. Wait a minute. Let's go down here to words. Well, we'll get here eventually. Okay. Okay, so we come out with the total load for this thing. 47,998 pounds. That's the tension load on the bottom. We divide it by the strength of the yield strength of the rebar. This would be a number, a 16 millimeter or a number 5 US. It's 96,000 pounds of stress rating. I didn't write the number in there. I'll just punch in this linearly through the calculator. Well, wait a minute. We'll wrote it someplace else. Okay, so if you divide those, it comes out rounded to the nearest thing. It comes out to a half a square inch of rebar. And we take one 16 millimeter rebar with an area of 0.307. So the area is bigger than one rebar. And you get the number of rebars required of 1.62. So that'll round up to 2 rebars. Doesn't sound like much, but you got to remember how tall this beam is. It's 2 feet tall with a 6-inch floor, so the beam is plenty stout. Now we're going to do the same calculation with a smaller rebar. We're going to go 47,998 pounds of tension divided by 101,000 K101K or K101. Yeah, K101 pounds of stress rating equals 0.475 square inches. And I got no idea why these cameras are reading at an angle, but they are. Oh, lovely. Now I know why I got it screwed up. Oh, no, okay, we're all right, we're all right. Yeah. When I came back from the going and looking at the picture, I jumped to the one that was for the beam turned the other way, I guess. Yeah, this is the second calculation. So we had the 23,986 pounds of total load times the half span. The moment it was 863,487 inch pounds. Okay, we're right. I haven't screwed it up yet. We're doing this for the beam laid flat. I just didn't make that clear. The first one we looked at the beginning of this thing was for the beam upright. And now we're looking for how many bars we need with it laid flat. And the number that changes is the distance down to the surface area to the center of the rebars. Where it was 19 thereabouts, now it's 11 when it's turned the other way. So 863,487 inch pounds. And that is the same exact number for the same beam turned flat as it was upright. The volume of concrete's the same. What's going to change is the distance from the surface down to the center of the rebars of the beam laid flat. Where it was 19 and a half, it's now 11.816. So we take our tension load, which we get when we divide those two things. It's probably written on the, yeah, there it is, 73,078 pounds. 73,078 pounds. 70,078 pounds divided by 96,000 pounds of stress rating. That requires 0.761 square inches of rebar at that rating. So 0.761 divided by the area, or by one rebar area of 307 equals 2.48. That would round up to 3 bars. And this line down here doesn't make any difference because that's figuring the spacing between them. You could put it in there and it'd tell you probably a best spacing to use, but it would depend on how it fit across the bottom of the beam. You're going to put them in that space, one near each end, and the rest of them pretty much evenly spaced across the middle. So we did this calculation for a 16 millimeter. We're going to do the same calculation for a 12 millimeter. What we're doing here is calculating how many, we're going to end up with how many linear feet of rebar, or how many pounds of rebar, whatever you want to go by, that the two different sizes of rebar do to do the same load. If your number of rebars is really crowded across the face of the beam, you might want to look at the one bigger and smaller, probably bigger. Anyway, we're going to calculate a second one. The load, the tension load is exactly the same. It's the same thing. We're just looking for a different number of beams. 73,078 pounds of tension divided by 101,000 pounds per square inch stress rating equals 0.724 square inches of rebar. 0.724 square inches of rebar divided by the cross-sectional area of one 12-millimeter rebar, which is 0.195 square inches, equals the number of rebars required of 3.71. That will round up to 4. So we need 3 number 16s or 4 number 12s to do the same job. Now, with the 3 number 16s, we rounded up by half a rebar. On the 12s, we rounded up by a little more than 1/4 of a rebar. So all else being equal in pounds, we have a much stronger beam with the 16s at 3 bars than we had with 4 of the number 12s. And also less to tie. So you figure out the weight of the rebars. Let's see here. I think this thing can get bigger. Or not. And that's typical. I don't think it got any bigger or easier to read. It just went to an advertisement. I can't drag it over. I searched Google for cross-sectional area of rebars. And it has, I use this chart right here, though I've got another one I use as well. Because you notice that this one does not have a number 10 or 10 millimeter rebar listed. Although where I buy my rebars in the Philippines, we can get either 9 or 10. I don't know if they have 6, but I know they have 9, 10, 12, 16. They have 18, not 19. Anyway, it got the bar sizes in millimeters and inches. It's got the nominal diameter. That's what these bar sizes would be. However, that's not the cross-sectional area. The place between the deformed things this is smaller because some of the steel went into making the ribs. So you have to use the cross-sectional area of the parts that actually get to use. What's up in the ribs, that's keeping it from sliding through the concrete. But that's not determining how much area you're working with for the stress. Guaranteed tensile strength. You'll notice that the number 4 or 12 millimeter is 101,000 pounds per square inch, or 700 MPa. That's the metric equivalent. The number 16 just below it, that's 96,000 pounds per square inch, or 660 MPAs. And then here next to it, we have the ultimate tensile load. And tensile modulus elasticity. You notice it's 5.91 on all the sizes. So obviously you can't change that. No use looking at it. You're looking for cross-sectional area of a particular size of bar and how strong it is. And you want it for square inches. So it says K, that's thousands, SI square inches. So this 101 is 101,000, and this is 96,000. And you'll notice that as the bars get bigger, the allowable stresses go down per square inch, but they're going up drastically on the square inch side, so the actual strength is going way up. Anyway, we also go to our friend Google and Googled density of concrete. 2,400 kilograms per cubic meter. That's what it weighs. And a kilogram is 2.2 pounds, so 50 some. Anyway, or 150 pounds per cubic foot. Doesn't say foot, but it is foot. And back down here. Conclusion. We already did that, actually. Conclusion is that you get more steel in your beam, and actually ultimately a stronger beam with the 16 millimeter rebar, because you round it up a lot more to get to the next higher bar than you did with the 12. You round it up much less to get the next, only about half as much. Oh. Road trip. Still opening this, I guess. I'm trying to get to the... Oh, it's saving. Man, clock's running here. Bad enough I'm so wordy. Now this thing's going to make it even worse. Being that this is drawn as a 3D solid, it's obviously calculating all those little ribs on the rebar. It's decided it needs to save again. Escape. There we are. Okay, what we're looking at here is how you use rebars. What we're looking at here is a slip form poured water cistern, 37,840 gallon. This one is, and you'll notice that there's a bent rebar here, and one comes from the other side. They overlap about 3 feet in the middle. No use cutting a piece of rebar off 15, 16 inches long and throwing it on the ground. Just put it in the wall. Anyway, this is the slip form with the rebars. What we're going to look at here, good a place as any. Let's just look at this. What you see here is running along with the edges nicked out. We call that a notched board. This is how we tie our rebar. We have 2 boards sitting on a floor someplace, or out in the grass out there, whatever you're doing. And you drop a bar in each one of these notches. And you have 1 or 2 more of these, depending how long it is. For 10 feet, you have 2 or 12 feet. And for 18 foot 6, you'd have 3 if you're a full length bar. and that spaces them exactly the way you want them. Now, this is the length of the wall, and this, I'll draw it on the side you can see, this is the height of the wall, right? Now you notice on the length of the wall, we cut the bars, but not in the center. We cut them at 11 foot and 9 foot, because we don't need as many bars of strength up here right at the water line of the tank. This is just airspace in the tank. So what we did, we wanted to get more bars closer together. And rather than having to waste half the bars, we cut them off center. And then we put them in a notch board. And so the red, blue, red, blue, red, blue, red, blue, all the way across matches up to these notches. Now, the bars that are going horizontal, again, back to the number 1 video of this 3-video series, they all have to stretch the same amount at any given point. So we're doing our major reinforcement as bands or belts around the thing. Down near the bottom, we have them closer together. And then they go a little farther apart. And then the slip form is going to be used 3 sets, 3 lifts. So there's 2 bars near the edge of the first lift, 2 bars at the start of the next lift, and then at the top up here, we do the same thing. So we get the full height, 4 foot of the form, and then we use the bottom hole in the top, and we get 3'6" and 3'6", and that apparently comes out to 128.9997 inches of wall height. These slip forms are the cheapest way to build a wall, a tank, or a house. If you've not got a crane to do tilt-up concrete, that is. But this is a solid concrete wall. The dimensions and sizes of all these slip forms is on a couple of other videos if you want to build a house this way. If you want to see it being done, look at Texas Filipino channel, TEXAS FILIPINO. He's from Texas. His wife's from Iloilo. They're building a house on the ocean. I mean, on the ocean. And he uses a 4-inch thick wall, which is gracious and plenty for an 8-foot high house wall. We use 7-inch. And the reason is we were pioneering this in 2014. And you have to get past building inspectors and things for certificate of occupancy. And if we'd have done a 4-inch concrete wall, it'd have been gracious strong compared to a 6-inch hollow block wall, 3 to 1. But they're going to look at that 4-inch wall and say, no, I don't know about that. And I didn't want to have it already up and then have to argue with them or go to court or something. So I took a regular wall, added the recommended thickness of render, didn't bother with skim coat because you're not required by law to have skim coat. Come out to close to 7 inches. So we just poured the wall 7 inches. Same amount of forms, it just takes more concrete. You run the mixer a little longer, and you throw another, I don't know, 5 bags of concrete to the pour day. And it's not insignificant, but it's not that bad. Anyway, that's the reason why we're probably going to put some videos out on building this water cistern. And that's why these bars look like they're different distances apart. It's because we want more near the edges where the load is high. It's the same thing, tension and compression. You have a lot more load right at the edge. Take a piece of paper. You want to tear that piece of paper, you put a little notch in it, and you tear it real easy. You try to stretch it apart, it's almost inhumanly possible to do it. Back to something else over here. For our foreman, we give him drawings printed off, and this shows the length of the individual slip forms. These slip forms are for the septic tank, the water cistern, fish pond, mausoleum, dirty kitchen. And that's why we have an 81-inch form instead of a 96 up here, because that's needed in the dirty kitchen. And we have some 4-foot sections. just because it allows us to do any of those things we want to build without building new forms. The forms for the system are basically all the forms we own. And these corners, they bolt together with 1/2-inch bolts. And then we have the plastic pipe spacer that goes in here between the foley boards. That gives you your wall thickness. Okay. So that's what you do with the rebars. And the beginning of this and the other 2 videos in this group, it just shows you how many you're supposed to have. If you're having a house built and it looks like you're really light on rebar, like if you see number 9 or number 10 rebars, what was 16? 40 centimeters on center, laying on the ground, not even supported. You might want to talk to your builder. Better to upset him than have a faulty house just level to collapse on you. If you see him pouring a slab that you're going to be sleeping underneath of, and the rebars are 20 inches apart in number 10s, you might want to look at the first video of this series on slabs. You'll see they're supposed to be much closer. We calculate them on the narrow span. However, if your room is square or even close to square, then you can use all of them in the calculation because there's not one being stressed more than another because on a square room. And if you're doing that, you want to do your weight or your load. Suppose we, yeah, we're all you can quit watching now. We're just talking. If I take this, the floor that's under this septic tank is from corner to corner, and I draw another line, corner to corner. It's going to make 4 triangles. If I take the weight of this concrete triangle, that can be the load that's on a beam on that side. And this triangle is a different shape, so it's a different area. It'll have a different load per square foot. So you can divide up a rectangular room into 4 triangles to figure out how much weight to assign to each one. Last word of wisdom. You design a house from the top down, because every time you go down a floor, all the stuff above it has to be counted, and it gets heavier and heavier and heavier. The strongest part's got to be next to the bottom, because at the top tie beam only got the weight of the trusses in the middle roof, and the next one you have to add the wall weights, and then add the floor slab, and then the next tie beams, and then the lower walls. So when you get to that tie beam on the bottom, it's going to be 3 times as big as the one at the top. Okay. Goodbye. Say your little prayer for us poor souls. Hope you're tired. You're allowed to leave a comment. Eventually I answer them. If you don't like it and you're going to give us a thumbs down, then I would like a comment. Tell me what, other than my presentation is a piece of crap. I don't need to know that because I've already been told plenty of times. I don't delete any comments. If you put one down, something ugly, it'll be there forever. And your name will be on it forever. Anyway, that's long enough for this video. Have a nice day.